These sections of your textbook deal with the mole and the periodic table. So to begin with, what is the mole? Is it really this fuzzy little creature that you see? It's not. I mean, it is, but in chemistry, we refer to the mole as just a really, really big number. So this number that you see at the top is 6.022 times 10 to the 23rd, and that is the mole. The mole is sometimes referred to as a chemist's dozen. Now, what do we mean by that? If I were to say, go to the store and get me a dozen eggs, well, you would bring back 12 eggs. Everybody knows that a dozen refers to 12. Now, there is a baker's dozen, blah, blah, blah. But for the most part, if I want a dozen, I get 12. So if I were to ask you, could you please give me a mole of atoms or a mole of eggs, you would come back from the grocery store with 6.022 times 10 to the 23rd eggs. So how big is this number? It is huge. Look at all those zeros. So if I had that many atoms, and I have that many atoms a whole lot, if you just put a tiny little bit on the balance, you probably have a mole. But if I were to have that many atoms, can you imagine having to write those zeros all the time? It's so much easier to just say 1 gram, 2 grams, than it is to say 602, 214, 179, and then all those zeros. And so because of that, we use this concept of a mole to talk about really, really big numbers. That's all it is. Big numbers of something. Atoms, molecules, eggs, it doesn't matter. Or my personal favorite, M&Ms. So let's look at some M&Ms as an example to really think about what is this idea of a mole. Okay, so for instance, I think we need to get to the important part of the matter here first. And that is, why do they call M&Ms fun size? The fun size is not the little bag. There is nothing fun about that. The fun size is that party size bag that you see right there. Now that I can get behind. But let's talk about M&Ms. M&Ms are wonderful little chocolate candies. So if I were to go and I were to take these normal size M&M bags and I were to open them up and I were to look at both a peanut and a plain pack of M&Ms. These have approximate masses, so you can see here there's 47.9 grams in this entire bag here. They're supposed to be, and then of the peanut bag there's 49.3 grams. So there's more mass inside of this peanut one. But if I open them up and I spread them out, what you see here in the picture is all of the contents of the plain M&M bag and all of the contents of the peanut M&M bag. I have less atoms in this package. Why do I have less atoms in the package if it's supposed to be the same number of the same amount per pack? Well, it's approximately the same mass per pack, not the same number of molecules. And the reason for that is, as anybody can tell you, these peanut M&Ms are a lot bigger, so they weigh a whole lot more. So what I wanted to do is I wanted to see, alright, what happens if I place 20 plain M&Ms on a simple balance? How much does that weigh? And in our case, it was 10 grams. But if I take those same 20 M&Ms, but this time they're peanut, now they weigh 43 grams, almost 4 times as much. So I have the same amount of M&Ms, but they weigh a different amount. And that's exactly how it is with chemistry. I could think about it as, why do the piles of candy weigh different amounts? Well, it's the same thing with atoms. Different piles of atoms would weigh different amounts depending on what atom it is, because every atom is a different size. They have different number of protons, they could have different number of neutrons, they could have different number of electrons. And so with that, you're going to get different masses depending on what atom you're weighing. And so even if you look at it from the side, you can tell that these peanut M&Ms are a lot bigger. So when we're talking about a mole of something, you have to remember that's just like saying 12 eggs or 12 M&Ms. You have some number of M&Ms. If they're smaller, then a mole is going to weigh a lot less. If they're bigger, they're going to weigh a whole lot more. And that's how it is with elements. So if we look here, water weighs 18 grams. It's pretty small, whereas iron is 55 grams for a mole. And so if I go weigh 55 grams of iron, or say 58.4 grams of table salt onto a balance, that's going to be a whole mole. Or helium. Helium is a really small gas. Just 4 grams, a balloon that weighs 4 grams containing helium, it is going to have an entire mole in it. It's going to have that many atoms in it, and that's a lot of atoms. So from the whole point of this whole lecture so far, I'm just trying to get you to understand that a mole is just a way of counting atoms. It's a way of saying, hey, this pile contains a mole of atoms. It contains a crap ton of atoms. Okay, this may be confusing. I like this line at the bottom, but it's similar to comparing a dozen elephants to a dozen mice. Although their masses are different, you still have a dozen of each. Alright, so keep that in mind when we look at our periodic table. So a mole is just a number. The mass corresponds with size. When we look at the periodic table, down here in the corner, you see the atomic mass. Now that's a weighted average because you have something that's called isotopes that we'll talk about later. But that's the mass. So if you have 1 mole of iron atoms, that mole is going to weigh 55.847 grams. That's all this number down here is telling you. So this video, you need to focus on this bottom number right here. But just kind of to go back a little bit and look at the history of periodic tables. This was invented by Dmitri Mendeleev. He made tables that look like this. He really focused on classifying, kind of coming up with patterns, and then he made his famous periodic tables, which have evolved into that periodic table that we know and love today. Alright, so let's practice. If I were to just simply ask you the question, what is the molar mass of each of the elements shown below? Another way of saying this would be, how much would 1 mole of each atom of each of the below elements weigh? And you would just simply look at their masses. Those are the average atomic mass. So if I have 1 mole of carbon, it's going to weigh approximately 12 grams. 1 mole of neon is approximately 20 grams. So when we're thinking about numbers or moles, you can go back and forth. You can either say I have 10 to the 23rd atoms, or I have 1 mole, but you use this Avogadro's number. That is at 6.022 times 10 to the 23rd power. That's Avogadro's number. So you can use that as a conversion factor to go from one to the other. And we're going to do a whole lot of practice of that. I think it's chapter 5. It might be 6. And then molar mass, you can use molar mass to go from how many moles do I have to how much does it weigh. And so we're going to be doing a whole lot of that later, but kind of the fundamentals of it is just asking this question that we did a second ago. If I have 1 mole, how much does it weigh? Would a mole of carbon or a mole of fluorine weigh more? Which one? And in that answer, it's fluorine, it weighs more. But what if I were to ask you, if I have 12 grams of carbon and 19 grams of fluorine, which one do I have more atoms of? Well, 12 grams of carbon is 1 mole. 19 grams of fluorine is 1 mole. So I'd have 1 mole of each, which means I have the same number of each of those atoms. So molar mass is a fancy way of just going from moles to grams and back and forth. Okay, so for next couple of slides, we're going to calculate molar mass, not of atoms because that's easier, but of molecules. In order to calculate molar mass, all you do is you add up the average molar mass of each individual atom. So for water, you just simply realize that you've got 2 hydrogens and 1 oxygen. Each hydrogen has a mass of 1.0794. And there are 2 hydrogens. So I have a total mass from my hydrogens of 2.01588. Then my oxygen. I have 1 oxygen and it has a mass of 15.994. So now I just add all those masses together and I get a total mass of 18. You can keep a couple decimals, you can keep all of them from this problem, but you only really need about like 2, maybe 3 decimals. But the important thing is you have a number, it's around 18, and you have a unit, and that unit is grams per mole. Those are our units for molar mass. Let's try another one. Carbon dioxide. You can try this on your own, or you can pause the video. We're going to do 4 examples. This is the second one. So with carbon dioxide, you have 1 carbon and 2 oxygens. So the mass of carbon is 12.0107. There's 1 atom, so 12.017. And then the mass of oxygen is about 16, and there's 2 atoms, so it's about 32. Add those together to give us a total molar mass for carbon dioxide of 44.0095 grams per mole. Number plus a unit. Now let's try this molecule, CH4. 1 carbon, 4 hydrogen. The mass of the carbon is 12.01. There's 1 atom. For hydrogen, the mass is 1.079. There's 4 of them. Add them together to give us a total molar mass of 16.04246, and that's grams per mole. Alright, now try this last one here. This one may look harder because there's more atoms, but it's the exact same problem type. You still ask your question, how many carbons do I have, how many hydrogens, and how many oxygens? Then for carbon, you take the molar mass of carbon, which is 12.017, times 12 atoms, gives you 144. For hydrogen, the mass is 1.00794. There's 22 of them. Multiply those together. Then for oxygen, the molar mass is 15.9994. There's 11 atoms, and that gives you a total mass there of 175. And now you add all 3 of those masses up to give you a total molar mass of 342.29648 grams per mole. You can also check your work by just simply typing in the formula for the compound and then putting MW after it for molecular weight. So that's C12H22011 space MW, and Google will tell you the molecular weight. But use that to check your work. Don't just do it. I think this is excellent practice for you. Alright, now your textbook has an example in it where it shows you 3 different ways to solve this problem. So this is a little complicated of a problem that it can be solved pretty simply, but it can be solved 3 different ways. And so it's saying if we were to burn a 10-carat diamond with enough pure oxygen, don't know why you don't want to burn up the diamond anyway, but whatever, how much carbon dioxide would be produced? Well, we already are producing enough carbon dioxide. Do we really need more? But they show you how to do it using mass ratios, atomic ratios, and moles. I find the most useful way to solve this problem is with mole ratios. We're going to be utilizing things like these mole ratios later in the course. So I'm going to show you how to solve the problem using mole ratios, just kind of to get you used to kind of seeing problems like this. But you could do any of the 3 ways to solve the problem. It's just moles are what I like best, and moles are what you're going to see over and over again later in this course. So here's our problem. I just pulled the last part of it and put it on the top of this slide. So this is our question, and we know carbon has a molar mass of 12.0107. That's from the periodic table, and we calculated earlier that carbon dioxide has a molar mass of 44.095 grams per mole. So when you're solving problems, you want to start first with the information you know. So in this case, we know that we have 2 grams of carbon, because it said that diamonds were, they're entirely made up of carbon. Okay, that's what it said here, of simply a pure form of carbon. So we know that we have 2 grams of carbon. Now we need to convert grams of carbon to moles of carbon. And to do that, you use the molar mass, which is shown here, as a conversion factor. So in that case, the mass of 1 mole, so this 12.0107 can be found on the periodic table, and that's grams of carbon, and that number goes on the bottom because grams of carbon is on the top. And then 1 mole of carbon, that's where the bottom part is. And so always it's molecular weight from the periodic table goes right next to grams, and then 1 mole is on the top. And it's always 1 mole. It's not 2 moles, 3 moles. In this case, oxygen, it's not 2 because of the subscript, it's just 1 mole. So periodic table number goes with 1 mole. Alright, and then you were to multiply that together, and that would tell us how many moles of carbon we have within this diamond. And then the problem says all of these moles of carbon are converted into carbon dioxide. So if all of that's converted, now that means that we have 0.166518 moles of carbon dioxide. So we've got all of that. But now let's convert it back from carbon dioxide moles. Let's go back to carbon dioxide grams. So in doing that, we set up another conversion factor. Go ahead and give it a try. Try and write a conversion factor that would allow you to convert from moles of carbon dioxide to grams of carbon dioxide. I hope you used this molar mass here. So we'd set it up to look like this. Now gram is on top and 1 mole is on the bottom. And that's because you want your moles to cancel out. You just multiply them, and now you know how many grams of carbon dioxide you have. So this is the method I like for solving problems like this, because it lets you think about, what is this mole? How does this help me get to useful information? So if I really needed to know, maybe I'm on NASA, I'm part of NASA, and I'm in a space, I'm in space and I'm running out of oxygen. And so you're trying to convert, carbon to convert whatever and make it so you can have breathable oxygen. Maybe you're saying, how long do I have to live? This would be the type of math that would get you to those numbers. Very simplified version. Alright, so with that, I hope you've discovered that the mole is a very special unit in chemistry. Chemists really couldn't get along without it. It is extremely important to the world of chemistry. So, finish reading this chapter maybe again, ask any questions that you need to, complete all your homework, and then take the first exam.